All right, so let us get started. This is a different screenshot of a different or extension to the previous flowchart which you have seen. Here, we look into multiple things such as comparing one population with the external standard. We will not do a deep dive on all these things, but I'm just trying to convey a message. Last time when we have looked into only these aspects, right? This part, wherein we compare two populations with each other. We have compared more than two populations, right? However, previously when we have done this exercise, we have looked into whether data are normal or not, and then we have jumped into variance test. We have checked whether variances are equal or not. However, we have not looked into whether external conditions remain the same. This is a new addition here. What do you mean by external conditions remaining the same? For example, if you're manufacturing, say, Coke, you're manufacturing Coke. You manufacturing Coke in Hyderabad versus you manufacturing Coke in Bengaluru will make a difference because the conditions would change, the labor would change, right? So there'll be a difference in the external condition. If I were to say that the external conditions are the same, then probably I need to manufacture in the same plant in Hyderabad location. Then the external conditions would remain the same for me to compare. This is a new addition here, which has been brought in. One sample t-test and one sample z-test. In addition to that, if the data are not normal, what do? We first check on whether there are any data entry issues or not. If at all the data are not normal, then you first check whether there is any data entry error while filling in the data. That's step number one. If you feel that data has been entered properly without any problem, absolutely, then step two would be try to transform the data. When I say transform the data, take the reciprocal of the data, or take the square root of the data, or take square of data, or take 1 by square root, or take 1 by square, or take log of the data, or take exponential of the data. Try to do some kind of a transformation on the data, and then try to plot the data and see whether the data are normal or not. Post transformation. If you still feel that data are not normal, then you need to go with these tests which are called as non-parametric tests. One sample sign test for median. Here we are going to test for medians. And in all other places, if you feel that the data are normal, you go ahead with testing on whether means are equal or not. Right here also it's mean. Here also it's mean. Here also it'll be mean. Right? However, your non-parametric test will actually test your median. In addition to these, you have another test called Kruskal-Wallis test, which was there in the previous slide which we have discussed. Okay, now let me get into this ANOVA. When we have discussed ANOVA previously last time, we have discussed about one-way ANOVA. What does one-way mean? And what does two-way mean, right? We need to look into that. ANOVA can be used to test equality of means when there are more than two populations. If you have greater than two categories or populations, then you go ahead and do ANOVA. ANOVA can be used with one or two factors. What is this one factor and what is two factor, right? If only one factor is varying, then we would use a one-way ANOVA. And here are the examples to explain you on what is one-way ANOVA and what is two-way ANOVA. When do you say that I have one factor and when do you say that you have two factors? Suppose we are interested in comparing the mean performance of several departments within a company. Here, department is called as a factor. Department is called as a factor, and all the department names within this department, these would be called as levels. Within that factor, you have different levels. Within a factor called department, I'll have names of the various departments, which would be levels. Let us look into two-way ANOVA. What is two-way ANOVA, right? You have two factors here. If you have two factors, you use two-way ANOVA. And here is that example. Suppose you're trying to measure or compare the mean performance of several departments based on shifts. So probably you'll have HR department and sales department, for example. HR department works in, say, day shift, night shift, and then afternoon shift. Your sales department also works in night, afternoon, day, afternoon, and night. Here you have two factors. What are those? One is your department. So all your department names would be called as the levels within that factor. Within this factor called department, we have multiple levels. And here you have shifts. Various shift, day shift, night shift. All these shifts are called as levels once again. Here also these are called as levels. Is this clear? Understanding of one factor, two factors. What is the difference between factor and a level? When do we use one-way ANOVA? When do we use two-way ANOVA? Is this concept clear? So Enoch has a question. If there are more than two factors, is it still two-way ANOVA? If there are more than two factors, you call that as MANOVA. It's multivariate analysis of variance. It's a different concept and it's considered to be slightly complex in the explanation and understanding. So we'll not get into that. But yeah, if you have more than two factors, you call that as MANOVA basically. Any other doubts, questions? Okay, Aditya has a questions. Two-way we have more than one input for a given y. Yeah. Yes, Aditya, that's right. Your inputs are called as your factors. Another name for your inputs is factors. Okay. So if you have no doubts, then okay. This is one more thing that I want to just quickly show you, and then we'll move on with ANOVA. Try to understand what is ANOVA in a lot more detail. Here is a small chart which explains on how do you deal with the data and what kind of test are you going to perform if both y and x are discrete. If you're comparing one population with external standard with some benchmark, you call that as one proportion test. If you're comparing two things with each other, you call it as two proportion. And if there are more than two populations with each other, if you're comparing, you call it as chi-square test. We've already discussed about two proportion test, chi-square test, right? Using case studies. So I'm assuming that you all know that. This is just one small addition. All right. Now let us spend some time in understanding what is ANOVA all about. So here is analysis of variance. Why is analysis of variance required to compare means of population? What is the principle of sum of squares? How to conduct the Anova test? What follow-up analysis should be done if Anova test is significant? So these are the various things we are going to discuss. Please pay attention here. Here is a case study. You can think about this as a live project also. Suppose there is a nutrition expert who would like to do a comparative evaluation of 3 diet programs. Here are the 3 diet programs. You have Atkins, South Beach, and GM. What your nutrition expert does is, she has say 60 people who have enrolled in that particular institute to become slim, right? This nutrition expert randomly assigns equal number of participants to each of the 3 programs from a common pool of volunteers. That means if you have 60, I'm going to assign 20 of them randomly. You know the concept of random. Close your eyes, just select 20 people, right? Whoever those 20 people are, you select them and you assign them to Atkins diet program. Another 20 people you randomly pick and assign them to South Beach. Another 20 people you randomly pick and assign them to GM. Right, so that is what your second point says. Randomly assign pool of resources to each of these diet programs. Now, suppose that the average weight loss in each of the groups or arms of the experiments are 4.5, 7, and 5.3. What does that mean? You have assigned 20 people to Atkins diet program. Once they do dieting, they are going to lose some weight. Say there are 20 people. Person 1 has lost 5 kgs, person 2 has lost 6 kgs, person 3 has lost 3 kgs, person 4 has lost say 3.5 kgs, so on and so forth for 20 people. If I take average of this, the average turns out to be 4.5 kgs. And I have South Beach, right? Again, I've assigned, or the nutrition expert has assigned 20 random participants to South Beach diet program. So once again, I list down the weight loss. For example, person 1 has lost 3 kgs, person 2 has lost 8 kgs, person 3 has lost 5.6 kgs, so on and so forth. You have this data. If I take an average of these 20 people who were assigned to South Beach, I get 7 kgs. And on similar lines, we will come to know anyways about the weight loss of 20 people assigned to GM diet program. If you take an average, it turns out to be 5.3 kgs. Now the question is, what should this nutrition expert conclude? Should she say that Atkins diet program is better, or should she say that South Beach diet program is better, or GM diet program? What should she actually conclude based on this data available? Here, what are you trying to do? You're trying to compare greater than 2 things, right? And if you try to compare greater than 2 things, then obviously we use Anova. Who is doing a good job, or which diet program is better? Atkins, South Beach, or GM? And you have the means, average mean of these 3 diet programs, weight loss of mean of these 3 diet programs. It looks better. Once again, we will not go with the pure numbers which are available here. We need to statistically evaluate this. What if this 7 kgs weight gain is because of outliers, weight loss? What if one person has lost 20 kgs, right? So we really don't know until and unless we statistically evaluate this, right? So let us understand this. There are two kinds of variations which matter. All these triangles assume are your Atkins diet program data, and the average of that would be 4.5. And then you have your GM. All these circles are your GM, and when I take the average of this, it turns out to be 7 there. And you have South Beach diet program. All these squares are rectangles, right? These are South Beach. If I take average weight loss of each and every individual, if I take average weight loss of all these individuals, I get 5.3. Now, if I take a grand mean, what do you mean by grand mean? Average of averages. So if I once again take average of 4.5, 5.3, and 7, I would get 5.6. Here, if you see, the variation is less within the group, within Atkins, within GM, and within South Beach. The variation among the data points is less, very less. However, if you look into scenario 2, the variation is high. Here also in GM, the variation is high. Here also in South Beach, the variation is high. Though the variation is high, it turns out to be that the means are the same. This is what I was telling. Why do we need to do ANOVA to check which diet program is doing a good job? What if there is this kind of variation? Say GM program, the weight loss is 7. However, the variation is too high. What do you mean by variation is too high? One person loses 1 kg, another person loses 10 kgs. Third person loses, say, 3 kgs, the fourth person loses 16 kgs. If my data set is in this way, that means there is a huge variation in the process. We need to consider all that before we make a statement on which diet program is doing a good job. It's not just the average. We need to look into standard deviation also. Given these two scenarios, in which scenario are you able to differentiate the groups properly? In which of these scenarios are you able to clearly demarcate and say that, hey, this belongs to Atkins, this belongs to South Beach, and this belongs to GM? Scenario 1, obviously, right? Because the variation within each of the group is less. Here the variation is more. Hence, for me to differentiate between Atkins and your South Beach and GM, it's difficult because everything is overlapping here. This part is overlapping and this entire part is overlapping there, right? So we need to look into scenario 1 is the best scenario, by the way. And one more thing is, if these three, right, if these three are more far away, say one is here, another is here, and another is here, will this scenario be easy for you to differentiate among the groups, or will this be easier? So if the distance between different groups is high, can you easily differentiate between two groups? Or if these three groups are closer to each other, then it will be easier for you to differentiate. This scenario, right? If your groups are far away from each other, it's easy for me to say that, hey, this group is different from that group. Take this simple example, right? If you have people from Tamil Nadu, people from Bengaluru, and people from Andhra Pradesh, for example, for you to differentiate between those three might be a little tricky. However, if I take Indians, Japanese, and Americans, if I take these three citizens, right, then it'll be easier for you to differentiate and say, hey, these people, those Japanese and Americans, these are all different people, right? That is what I'm saying here. If the distance between the groups is more, you'll be easily able to say or differentiate between the groups. So there are two concepts here. One is within group variation, within that group, how are the things varying? Obviously, the variation here in scenario 1 is less as compared to your scenario 2 where the variation is more. Here also variation is less as compared to this where the variation is more. This is called as within group variation. Also, we have between group, which is grammatically incorrect. Right? Between is between two, among is between more than two. Anyways, statistically, that is how we use. That is a word which you use. So one is within group variation. Another thing is across group variation. This across group variation should be high, right? And that is what is mentioned here. Easier to identify variation across programs if variations within programs are smaller, will be easier for you. Hence, this method is called as analysis of variance. Though you're dealing with the means, though you're trying to check or comparing the means, you call this as analysis of variance because you're dealing with the variance within group and across group. Now, that's the intuition, and then we are going to formalize now. Take one data point here, right? Any data point. Say weight loss of person 1 in South Beach Diet Program. Will his weight loss be exactly equal to the average weight loss? The average weight, what is the average weight loss for South Beach Diet Program? Let me go up here. Average weight loss for your South Beach Diet Program is 5.3, right? It's 5.3. Now, does that mean that all the 20 people who have been allocated to South Beach Diet Program, their weight loss will be exactly equal to the average weight loss? What do you think? Just give a thought. No, right? On an average, the weight loss of 20 people is 5.3 kgs. This does not mean the weight loss of all 20 people would be 5.3, right? It would be different. And how far away each point or the weight loss of each person is from the average is called as error. This is called as error. How far away weight loss of each person from the mean is called as error, EIJ. Okay. Now the second thing. Say you have an average weight loss. Say average weight loss of South Beach is 5.3, your GM is 7, and Atkins, I believe it's 4.7, if I'm not mistaken. Let me check that once. Yeah, 4.5, 5.3, and 7. 4.5. This is the average weight loss of the 20 people who have followed South Beach Diet Program. And 7 is the average weight loss for people who have followed GM diet program, and average weight loss is 4.5 for Atkins diet program. Grand mean is, I think, 5.6, right? Or whatever value. Grand mean is average of these three. Average of these three, you are getting some value, say 5.9 or 5.6, whatever be it, right? right? So your grand mean is 5.6 does not mean each of the averages would be equal to 5.6. There would be some variance. There would be some variance. There would always be some variance. That variance is represented using TI, which is called as treatment. Okay. Hope it's clear until here. What you're doing is you're taking the weight loss of each and every person. You're comparing it with the average weight loss. Right? And that you're calling as error. Then you're comparing the average weight loss of each and every diet program with the overall average of all 3 diet programs. And this is called as treatment. Here we have treatment. Okay. Now, if I want to find out the total, if I want to calculate the total variation from here until here, then it's nothing but summation of TI, this zone, plus summation of this, right? If I add EIJ plus TJ, I'm going to get the total variation. Clear? Is this clear, friends? At least until here. Is it clear? Yeah, only Enoch has responded. Can others also please try to respond? Yeah, it's clear. Yeah. All right, Monica. So everyone is clear with this. Great. So if we simply take the summation, right? Sum of square total, if I'm just squaring that. Now, I think Aditya was asking on when we calculated variance, right? We have used this formula, summation of xi minus mu whole square divided by n. I think Aditya was asking on why do you square it? We square it because otherwise the value, if you calculate and say, it will become 0. On similar lines, we are squaring this. And this, when you square it, you'll get sum of square treatment and sum of square errors. Here, let us interpret this. As and how the number of participants increase. Say we had 60 participants who participated in this diet program, and out of 60, 20 were assigned to South Beach diet program, 20 were assigned to say GM, and 20 were assigned to Atkins, in that way, right? Now, if I increase this 60 to say 100, what am I effectively doing here? So I increase to 120. So what am I trying to do here? I'm increasing the value of n, right? Number of people participating. I'm simply increasing the n value. If I increase the n value, what will happen to your sum of squares treatment? Will it increase or decrease? Increase. Yep. Now, if this is one data point, if this is a weight loss of one person, you get one EIJ. So for 60 people, you'll get 60 such EIJ values. And if I increase from 60 to 120, I'll get 120 EIJ values. And I'm adding all 120 EIJ values by squaring that. If I do so, will this value increase or decrease? This component, sum of squares error. increase, right? Because number of EIJs are increasing and you're also squaring those, so it will further increase. This is considered to be a bad situation because your sum of square total is getting influenced by the number of data points, number of people participating. So your results will not be the same. Your results are going to vary depending on how many people are participating. Now, I don't want such a situation wherein number of participants participating in the diet program is going to influence on uh, in if I were to say which diet program is doing a good job, the number of participants is influencing that decision, which is a wrong thing. So what do? I try to do some transformations and ensure that such kind of thing does not happen. For that, what am I doing? Say you have n subjects equally divided into R groups. Say I have 60 people, n is 60. They are equally divided into R groups. So I'm equally dividing them into 3 groups. Just take an example, right? Under such circumstance, what I do, if I want mean square treatment, right, then I'm going to take sum of square treatment and then divide it by r minus 1. Some transformation is happening and I'm dividing it by r minus 1. This will ensure that as and how the number of data points increase, this value doesn't get impacted. Some kind of transformation. If you do not understand, that's okay. And mean square error, here also you're doing some kind of transformation and ensuring that as and how the number of data points increase, your EIJ value does not get impacted. That is MSE. Now, if I take a simple ratio of MSTR and MSE, I'll get the F value. And we have discussed about Z table, T table, and all that, right? On similar lines, you have something called as F distribution also. That is how you calculate that. And in order to calculate the p-value, it is probability of the actual F, yeah, random variable F being greater than or equal to this value F. We have previously discussed this concept, right? Probability of X greater than or equal to small x. And then, you actually from that, you will get the p-value, right? You compare the p-value against alpha value. And if your management doesn't give you any alpha value, what is the alpha value that you tend to choose? What is the alpha value that you tend to choose? 0.05, 5%. There's a 5% chance that you might go wrong, kind of. So if p is less than alpha, you say that this is p low. If p low, null, go. That means you're going to reject the null hypothesis. And if you reject the null hypothesis, you'll go ahead with the alternate hypothesis. You say not all means are equal. Same example. Here, instead of 60 participants, they have taken 12 participants, divided into 3 groups, and you have total 36 people, right? Now, this is how you calculate the ANOVA table. Degrees of freedom, how did you get diet as 2? It's R minus 1. Here, how did you get 33? It is N minus R. Then we have the formula for sum of square, and then you go ahead with mean sum of square. If I divide these two, I'll get the F value, and F value probability greater than or equal to F, you will get this value. And you compare this p value with your alpha value. Here in this case, it's less than alpha. So P low, null go. Clear? So probability of making a mistake is less than 4%. Here it's 0.039, right? If I round it off, it'll become 0.04, which is nothing but 4%. Clear? Let me know if you have any doubts here. Let me know even if you do not have any doubts, so that we might proceed with the next analysis. Okay, Vijay has no doubts. Aditya, Enoch, Rajiv, clear Rajiv? Okay, let's proceed. Okay, let us proceed in that case. Now we are entering into a zone which is called as